Hi, I'm Neela Gupta, the Chief Engineer for the Terraplanes, the University of Maryland's 2021 Design Build Fly team. In this video, I will discuss the design of our plane and show how it performs in flight. Here are some images of our current aircraft, whose features and subsystems I will now detail. Our aircraft's major dimensions are as follows. It has a length of 72.63 inches and a height of 27.91 inches, 2 inches more than in the report due to an increase in vertical stabilizer size. The wingspan is 60 inches. The aircraft has an empty weight around 13 pounds, excluding the batteries used to power the systems. Since each mission has different objectives, the gross takeoff weight varies as follows. Mission 1 is 15.17 pounds, Mission 2 is 21.11 pounds, and Mission 3 is 15.5 pounds. Our aircraft's control surfaces consist of flaperons, an elevator, and a rudder, each of which have a plus or minus 20 degrees maximum deflection. Flaperons were selected at the request of the team's pilot. They are hinged at 80% of the wing chord and span 75% of the total wingspan. The elevator and rudder are both hinged at 70% of their chord. The elevator is split into two halves and spans the entire length of the horizontal stabilizer, while the rudder only spans 8.25 inches of the total 10.25 inches of the vertical stabilizer. The flaperons are each actuated by 76 ounce-inch servos, while each half of the elevator and the rudder are actuated by 25 ounce-inch ones. The propulsion system is detailed as follows. LiPo batteries were chosen for their high energy-to-weight ratios. To maximize capacity, we used two 6S 4500 mAh packs in parallel. For our motor, a 295 kV brushless outrunner rated at 2700 watts was selected, accompanied by a 130 amp ESC. As for the propellers, a 20 by 13 inch propeller capable of producing 18 pounds of static thrust will be used for missions 1 and 3. For mission 2, we will switch to a 21 by 14 inch propeller for its increased static thrust output of almost 21 pounds. This ensures thrust-to-weight ratios of at least 1 for each mission and the ability to fly at high speeds. Drive components were selected using PropCalc, a fixed-wing RC aircraft drive simulator within the eCalc suite. Possible propulsion configurations were picked out, and the most important propulsive performance characteristics were determined. Performance trade-off analyses were conducted for every configuration, which then allowed for the optimal components of each mission to be selected. As shown in the videos, the performance of the selected components were verified on the testing apparatus built by the propulsion team. In the design of the wing, we performed a trade study on wing taper. An analysis was performed on taper ratios ranging from 0.3 to 1 while holding wing area constant. We found that we could only achieve a maximum 2% increase in aerodynamic efficiency. This was not worth the manufacturing complexity of a tapered wing, so a straight wing design was selected. The entire aircraft utilizes a rib spar construction due to its lightweight design yet ample structural support and ease of manufacturability. Two carbon fiber box beams serve as spar support based on torsion and 4-point bending tests. The front landing gear is a combination of a purchased oleo strut and a custom aluminum strut. The rear landing gear uses a purchased carbon fiber strut that gives enough flexibility to absorb the initial contact with the ground while still being strong enough to survive hard landings. The empennage design is similar to that of the wing, but uses smaller pull-treated carbon fiber rods in place of box beams. Two additional carbon fiber rods are utilized on the underside of the fuselage to increase rigidity. Using an optimization code that the team developed, we determined that the optimal plane is one that carries 18 sensors, with each sensor being 13.25 inches long and weighing 0.33 pounds. The PLA sensor has a box fin after the sensor CG for stability and carries a light control circuit, a 1S battery, 3 high-power green LEDs, and an extra weight for sensor balance on carbon fiber rods. The sensor is connected to the aircraft via a braided PET cable with enclosed wires for LED control. To deploy and retract the sensor for Mission 3, a motor wraps and unwraps the tow cable on a spool within the aircraft. In flight, the sensor is housed below the tail in a foam funnel used to guide the sensor back into the aircraft on retraction. For Mission 2, the simulators were 3D printed from PLA with mounting locations for dense ball bearings to bring the simulators up to required weight and adjust CG location based on testing results. The sensor container is made from foam for reduced weight and flexible plastic end caps to reduce damage during drop testing. With this design, we believe our plane will be a high-performing one that will fly at the flight conditions listed in this table. These numbers were obtained using a modified version of the optimization code and vary from the report due to improvements made over the past 2 months. At these flight conditions, we predict that our plane will achieve a very competitive mission score of 4.95. The score breakdowns, as well as comparisons to the highest scoring teams, are shown in the table. The scores assume the highest scoring planes carry 25 sensors that are 15 inches long and weigh 0.5 pounds. Now we will show how our plane performs during the ground mission and mission 3. First, we can see through these pictures that our constructed plane almost exactly matches the 3-view drawing presented earlier. The only difference is that our front landing gear had to be reconstructed due to it being destroyed during a flight test. This fix increased the angle of attack of our plane on the ground slightly. Now, we will show the functionality of the sensor and its related systems on the ground. Through a switch on the main transmitter, we turn a DC motor on to unwind the tow cable and deploy the sensor. While one of our members is supporting the sensor, he is not pulling it, which is proved by the slack in the cable. Using another switch on the transmitter, we turn on the light sequence. Here, you can clearly see the bright green LEDs turning on and off in a sequential pattern. Finally, using the same transmitter, switch for deployment, we turn on the DC motor to turn in the opposite direction to retract the sensor. Again, our team member supports the sensor but is not pushing it back in as the cable will buckle under any compressive force. Next, we will demonstrate takeoff. As you can see in this clip, our plane tracks fairly straight along the runway. We can also see that it takes roughly 7 plane lengths, or 42 feet, for a plane to achieve liftoff, which satisfies the maximum 100-foot takeoff requirement. Next, we will show our plane landing. In this video, you will first notice that our plane can easily make a well-controlled descent, even with strong, varying crosswinds. The actual landing contact with the tarmac is smooth. The landing gear holds up well, and bouncing is kept to a minimum. The plane also tracks straight almost the entire time as it smoothly coasts to a stop. Now, I will begin showing sensor functionality in flight, beginning with deployment. While it may be difficult to discern, you can see that the sensor is initially entirely inside the plane. When the deployment switch on the transmitter is flicked and the plane climbs a little, the sensor falls out due to its drag and gravity. The drag helps the sensor maintain its orientation while it deploys. The pilot switches the deployment switch off once the sensor is at its full 12-foot distance. In these next clips, we demonstrate flight with the sensor deployed. You can clearly see the sensor has little to no effect on the stability of the airplane. Our plane never experiences any noticeable orientation perturbations. When the airplane is flying in straight, steady level flight, the sensor remains extremely stable and maintains its orientation well with minimal rotation. Most sensor instability occurs during turns when the sensor is not directly behind the airplane. This instability is also completely restricted to oscillations in pitch. There are no undamped instabilities or rolling ones. Overall, considering the sensor flies in the turbulent prop wash flow of the airplane and likely experiences varying winds, our sensor remains aerodynamically stable to a satisfactory degree in flight. As additional proof, we can see in the still image that the marker to indicate that the sensor is fully deployed is visible and that the lights on the sensor are visible when active. Finally, I will show retraction of the sensor in flight. The sensor clearly begins fully deployed. When the transmitter switch is flicked, the DC motor turns on, reeling in the tow cable and the sensor. Throughout this operation, the sensor still remains almost perfectly stable. We can see that our retraction approach is extremely successful as the sensor is pulled entirely within the rear fuselage section of the plane. As additional proof, here is another clip of a successful retraction. This concludes the Terraplanes video report for the 2021 AIAA Design Build Fly competition. Before I end, I would like to thank our sponsor, Millennium Engineering and Integration, the University of Maryland's Aerospace Engineering Department, our pilots Nick Rem and Peter Rysek, our advisor Dr. Sung Lee, and most importantly, all the other team members. All of your contributions were a vital part of this year's successes. I hope you enjoyed the video, and thanks for watching.